You have to go. Actually, it's the hands.
Yeah, I told her it was on here. But I just did it. But no, that's part of
Oh, this one? I have that. I'm still trying to figure it out.
Point five. Yep. Times 0.5. Yeah, exactly.
Get my answer off.
All right, guys, I'm starting to catch up to you here. So if you want to double check what you got so far. Is that what you guys got for part A? Like 543 up to 0.619 roughly?
Yes.
Yeah.
All right. So then we are 90% confident.
95.
Sorry. That the interval 54.3% to 61.9%. These are true percentage of people that voted. Now, so from your analysis, based on what people told you, it looks like the percentage of people that voted has to be, more than 54.3 in between these two.
Yeah.
You with me so far?
Yeah.
And there's like a 5% chance I'm wrong on that, right? And by the way, to be 100% confident, your interval would always have to be negative infinity to infinity. So it's telling you, hey, this life, you can't ever be 100% confident. Yeah.
I'm a little confused of how you got 1.96.
Two different ways. The quick way for certain numbers is just to look at the little baby chart. Confidence level 0.95 as a value of 1.96. Now, where does that come from? 95% in here means how much outside? 5%, so 2.5% on one side. If I look up 0.025, I get 1.96. That's where it comes from. So you know me by now. I might give you some of these, but then I'm going to ask you to make an 87% confidence interval. And then you're going to have to know how to do it the old-fashioned way. Actually, look it up, right? But if I give you one of these, you just take it from here, should you? Okay. So part B, if my analysis seems like it's got to be in this range, and it actually, in reality, is this range, some of the people I talked to must have Lied to me. There you go. I like it. It's just, they lied. Why? Because they sucked. No. So, what is most likely true about some of the people on your sample? They lied because my analysis showed it's supposed to be more than 49%. But it was based on what they told me, right? So that really just says observation always is better than relying on somebody's, what they say. Right. Okay, cool. So number 2, this is my fault, I didn't write this too well, but I'm still having a 95% confidence interval. I don't have a clue about p hat and q hat. I don't even know what the hell this is talking about, but the math can still be done.
50-50.
Yeah, exactly. So n is 1.96 squared, 0.5 times 0.5 divided by, what's e? 3%, which is what is a number? Everybody's like, 3 is a number, Jeff. No, but 3% is not a number. What's 3% is a number? 0.03. Right? Math is like, that's nice you humans made percentages up, but give me the freaking number. That's what math means. Math means the number. And when you do that, what do you guys get? Everybody's redoing it. Like, yeah, I get 1067.11 blah blah blah, so it would be how many? 1068. I like it. So depending on if I'm in a company, a large company, that's no big deal. If it's only me and somebody else, that might be too many people to try to talk to. So that's why it's a feasibility study. How feasible is it to be that accurate? Well, it depends on how big 1068 is to you. Yes?
And why did you use the 1968? I'm sorry.
That was I left that off. That was my bad.
Oh, okay.
But I have to tell you at what confidence, and that I just left it off. It's my fault. So the point, now let's do part B, and I really want to go back and make sure you understand. This might not make the most sense, like if you don't know, like if I said what's probably going to snow tomorrow, I wouldn't say, well, I don't know, let's say 50%. I mean, that doesn't make any damn sense. So there's got to be a better reason why we use those, and there is. On part B, I got to do that first, and I can show you. What is p hat now? I know it's 0.23, so what's q hat? So it's the same work I just did, except now I know what p hat is, so I know what q hat is. Over 0.03 squared still, right? And let's see, what do you guys get now for that? 756, I like it. 755.9, blah, blah, blah. So 56, Jeff? Good job. 756. So do I need more or less people? Less. And let me ask you this. If there's something you're not sure about in your problem, how do you cover yourself for that? You take a larger sample. So mathematically, 0.5 is what always makes n the biggest. So now it makes more sense. If you don't know what p hat and q hat are, too bad for you. You better take more people. You got to take the most people you would have to. And what mathematically makes the number the biggest? 0.5. Anything else for p hat and q hat will be less than 1068. So that's why what we normally do is we go take a sample of 50 people, and we get a preliminary p hat, and then I plug that value in so I get a real idea of how big of a sample. Not start with nobody. I start with a small study, and then I see how many more people do I need to go get to make it this accurate. Okay, cool. Let's see, what time we got? Let's see if I can push it a little bit. Some of you guys are stacking up, spoiling you. So I'm not even 12 yet. Of course, most of you are like, I have no idea what time it is, Jeff. It just feels like it's time to go. All right, so I do want to talk about the next idea a little bit. Just to get us started to think in that direction. So this is related to a question I think you asked earlier, Dean. Section 8.1 is always assuming, and they always give us the population standard deviation. And I did talk about why that might be something that's known, because maybe I know something, I'm just taking a smaller subgroup, so I already know what everybody's standard deviation is. But in reality, I normally don't know shit. I go take a sample of whatever, and I don't know. I'm just taking a sample just to see. So I don't know mean, I don't know standard deviation, I don't know crap. So I'm going to get X bar from my sample, I'm going to get S from my sample, and then I'm going to try to do some of the same stuff we've done. The problem is, if there's a part of my work that I'm not sure about. So if there's a population, there is a sigma. Is that cool? There's a population standard deviation of whatever it is. Is that cool? So I take a sample and I get S from my sample. Is S the same as sigma?
Not necessarily.
In fact, I would put money on it not being the same, right? And I'm a teacher, I don't make a lot. So if I put money on something, that means something. More than likely, any sample standard deviation is not going to be the same as the population standard deviation. Let me stop there for a second. Is that understood? So what I need, I really want this to make sense. Let me just give you the broad idea that makes the most sense, and then I'll narrow it down. So for example, if I know sigma, and I want a 95% confidence, I would use a z-score of 1.96. Is that cool? All right. And that makes my confidence interval like this wide, let's say. And if I wanted to be 90% confident, it wouldn't have to be as wide, and so forth. Is that cool? Okay. So if there's a part of my work that I'm not sure about, in this case, namely the standard deviation, I don't have the right one. I just have S. I don't have sigma. Do I want my confidence interval to be bigger or smaller to cover me for that fact? So if there's something I don't know, let's say, stay with me through this fish analogy because it's the best thing I can think of. So I got my net ready, and I know there's a certain type of fish I want to catch, and I think I know how far he normally swims. That's kind of related to the standard deviation. Are you with me? So the less sure I am about the range that he swims in, if I'm less sure, should I use a bigger net or a smaller net? Bigger freaking net. If I use a smaller net and he goes further than I thought, I'm not going to catch the dude. I really want this to make sense. If there's a part of something that I'm not sure about. In this case, the only thing left that I'm using I'm using sigma for this, for the problems we just did. I normally don't know that. I've got to use, oh shit, that means I'm using something that I don't know if it's right or not. In fact, it's probably wrong somehow. So to cover myself for that, I catch more data. I just go a little further out. I really want this to make sense. So the number I use in the formula, this formula or this percentage, actually the percentage, we'll talk about that. This formula here, the number I use right there is going to be a little bigger than this. So that I have to go further out a little bit. Anything that makes my certainty less pushes me further out. If my sample gets smaller, doesn't this whole thing get bigger? It's going to push me out more. When I get my sample smaller, I'm less sure about what I see. It's going to make the confidence interval bigger. If I don't have this, if I only have S, my confidence interval should get a little bigger. So the way we do that, let me make sure. You guys, does that make some kind of sense a little bit? I mean, if there's something you're not sure about in your calculations, how do you cover your ass for that? You make this a little bigger. Right? And actually, you can think about it as actually physically covering your ass if you want to. Make it a little bigger. You with it? I'm not sure if it's covering my ass. Let's make that bigger so I'm not showing my ass in it. So I really want this to stick with you, this idea. So here's the thing. What we do then, and does this make sense? When are you more sure about this? If I have a larger sample, right? So the bigger my sample is, the number I'm going to use instead of this number it doesn't have to be that much bigger. So if I have a very small sample, I'm going to have to use a much bigger number than 1.96 to cover my ass. The bigger my sample gets, I don't need it to be that much bigger than 1.96. Just be a little bit bigger than 1.96 because now I'm more sure about this. The bigger my sample, the more sure I am that is close to that. Good. So now we get very specific. I want to give this. I'm just going to give this to you and let's see what happens. This, I can't control how you react to this, but So we can't use officially the normal distribution anymore. We use something that's a little bit, now don't freak out on me. It's very close to the normal. All it does is, depending how big the sample is, it takes this and makes it a little bit bigger. Right? And then the bigger the sample gets, the closer it gets to 1.96. I don't need it to be as big anymore. So let me just give this to you. Don't freak out too much. We're going to talk about it a little bit and then I'll let you guys out. Anytime.
Well, Rogue One is coming out on December 16th. It was a teaser trailer. Can we have one more? Well, it was like a minute. But I was here no Vader, no.
All right, guys. The first quick little thing is it? Oh, yours is there. Sorry. Eventually, it's going to get to you. And it's moving again. Okay. First quick little thing, and I'm going to spend a little more time on this next time, but for right now, see where it says degrees of freedom? Degrees of freedom is equal to the sample size minus 1. So just, for right now, just take that. Right? Say like, why, what the hell? Just add 1 to that. So no, it exists for a reason.
Is this a don't write on it physical reason on the test?
Yes, good. So some of you guys have picked up on that already. Obviously, we're going to use this on the test, so don't put notes on this. Right? You're going to turn it in with a test, so don't put any far too useful notes on this. So real quick, other part of this. When I make a confidence interval, what would it? Can you draw a confidence interval? What would it look like? What am I going to do? A confidence interval. What am I going to make up here? You can do this. What would it look like? You're like, I don't know, Jeff, it's numbers. No, I would start in the middle and go where? Out. So many. So that's a confidence interval right there. Is that cool? Can you tell me, what's it look like? How many tails did I just make? 2. I love it. So see on the top where it says 1 tail, 2 tails? Confidence intervals, I'm always going to look at 2 tails. So if this is 0.95, how much is in 2 tails? 5. All right, so look at the 2 tails, 0.05. You guys with me still? So that means the 95% confidence interval. I like it. So that column here. So look at the very bottom of that column. What number do you see? Holy shit. All right. You guys, what sample size does that relate to? Large. I love that. What's large mean? I don't know. It just means large. So it actually, to a point, it is kind of subjective. But now look, what happens as my sample size, and I know this is 1 off from the sample size, but let's just say this is basically the sample size. Is that cool? That's really 1. So as my sample size gets smaller, I'm less certain about the standard deviation that I calculate. Therefore, this score has to get bigger to make my confidence interval bigger. I really want this to make sense. So the work, this is the beautiful thing. I know some of you guys, when I said there's a chart, there's a different distribution, you're all like, God, I was just starting to understand some of this shit. All the work is the same. I just don't put a z-score here. I put a t-score there. This is the t-score chart. And they're built off of z-scores. They just make them a little bigger, bigger, as my sample size gets smaller, just to cover my ass for the fact that I know it's less and less sure about the standard deviation. Please let that make sense. There's a whole section devoted, it's section 8.2 that I skipped, to this idea. The work is exactly the same. You just have to be careful. If I say I took a sample of size 37, what am I going to look at? 36, because degrees of freedom is n minus 1. And then you look over and you say, if you want a 98% confidence interval, which one are you going to look at? 98%. Yeah, has 2% in the tails, right? Now, real quick, if you actually, like here, if you actually said it was 0.025 there, then that's the amount in one tail. Isn't that the same freaking column? So if you make a mistake if you go on one tail, well, it's going to keep you in the same column, right? So 98% would be 2% and 2 tails, 1% and 1 tail. You almost can't go wrong. And then you just kind of go down here until, what did I say? I forgot what I said. 36 down there. And that would be the number you would put in the formula. It's just a different chart to get a number. Instead of the z-score chart, you look at this chart. I like it. And you notice, I don't know if anybody notices this, the little baby chart only has 3 things. This has 1, 2, 3, 4, 5 things. So if I want an 80% confidence interval, let me see if you guys understand. Where are z-scores? I know this is a t-score chart, right? Where are the z-scores on this chart, though? These are all z-scores. Don't these look familiar? 2.33. They just made it a little more accurate. 2.575. Well, it's actually 2.576 to be really accurate. We used that for 99% once before. 1.96, we used that today. 1.645, that's come up before. 1.282, that ain't come up because you normally don't do an 80% confidence interval because then there's 20% chance you're wrong. You normally don't want to be that. But they put it on there just in case. I like it. So that was unbelievably quick. But I at least wanted that in your brain to just kind of simmer until I see you next. All right.
Can I see it?
Oh. Thank you. Please do give me back my calculators. Thank you.
There's a question.
Yes.
You put 0.5 because that's the 0.5 that's the.
Yeah, we don't know. That's our best guess. But also mathematically makes that come out the biggest. Anything else I put there. So if I have an idea of what it is, it's going to make that smaller. Because now I know something that I should have to do less work.
That would just be like them saying yes and them saying no.
Exactly. 23% said yes, 77% said no. So if I knew that, how many people would I need to be within 3%? Less people than here. If I know something. If I don't know shit, I need more people. If I know something, I need less people.
Yeah. And this one, this is for finding the margin of error. This is what the formula is.
Yeah, that's the, E is the margin of error, or the error bound, sometimes they call it that. Yeah.
Oh, okay. Thank you.
Sure.
Okay. So are you always rounding up with these?
Yes, because
No
that's,
matter if it's a 0.1 or...
totally, because it's got to be at least that to be within that much error. So if you ever round it down, oops, now you're less than that. That's no good. So you always round that up. Yeah.
And then with